In section 2.8, we look at transformations of the graph of a function. And for this section, we are primarily going to focus on three basic functions. We're going to look at transformations of the graph of the function f of x equals x squared, which is this parabola. Also, f of x equals the absolute value of x, which is this V-shaped graph. And finally, f of x is equal to the square root of x. These are three very common functions, and everyone should know how to graph these functions, how to sketch a graph, that is, without having to plot points. All right, let's get into the transformations. First, let's discuss vertical shifts of the graph of a function. Suppose we know that the graph of f of x looks like this. If you want to graph f of x plus a positive constant c, that is going to shift the graph upward by c units. And if you do f of x minus c, that will shift the graph downward c units. So as a summary here, if we know what the graph of f of x looks like, the graph of g of x, defined to be f of x plus c, is simply the graph of f of x, but shifted c units upward. And the graph of g of x, defined by f of x minus c, is the graph of f of x, but shifted c units downward. Let's take a look at an example. In our first example, we're going to look at graphing f of x equals the absolute value of x, and g of x equals the absolute value of x minus 2. And they ask us to first do this by making a table of values for each function. So we'll go ahead and do that. So for the function f of x equals the absolute value of x, we're going to make a table of values, and the x values I'm going to choose here are going to be x equals -3, -2, -1, 0, 1, 2, and 3. And you don't necessarily have to graph this many points for this function, but we'll go ahead and go with what they asked us to do here. Now, f of x is nothing more than the absolute value of each of these numbers. So the absolute value of -3 is 3. Absolute value of -2 is 2, absolute value of -1 is 1, and so on. So these numbers represent the absolute value of each of those x values. Now let's go ahead and sketch a graph. So here I have a table, and we're going to graph all of these points. So we have the point -3, +3, -2, +2, -1, +1, 0, 0, 1, 1, 2, 2, and 3, 3. And if we connect those points, this is what we get. And so this is the graph of f of x. Now they want us to graph g of x, which is defined to be the absolute value of x minus 2. And they want us to do it the same way by making a table of values and plugging in the same values that we plugged in for f of x. So all we're doing here is we're taking the absolute value of each of these numbers, and then we are subtracting 2. So for example, the absolute value of -3 is 3, and 3 take away 2 is 1. The absolute value of -2 is 2, take away 2 is 0. Absolute value of -1 is 1, take away 2 is -1. And the absolute value of 0 is 0, take away 2 is -2. And then when you plug in 1, you get -1. When you plug in 2, you get 0. And when you plug in 3, you get 1. And now let's just sketch these points. And when you do that, you can see that g of x has the exact same shape as f of x, but we have taken the graph of f of x and we have shifted it downward 2 units, right? Every point on the graph of f of x was shifted down 2 units. Now, of course, we could have graphed this much more rapidly if we just notice that g of x is defined to be the absolute value of x minus 2. And that minus 2 is what shifts the graph down 2. So this is an example where you can get the graph by doing points, but really if you knew what the graph of f of x looked like, we knew what the graph of g of x was going to look like without having to graph all these points. Next, let's talk about horizontal shifts. So if I have the graph of some function f of x, the graph of the function f of x minus c is going to shift the graph to the right c units, and the graph of the function f of x plus c will shift the graph to the left c units. So it's a little bit counterintuitive because when you have an x minus c, notice that it shifts to the right, and when you have x plus c, you're shifting it to the left. And the difference between what's happening here versus what was happening on the previous page is that on the previous page, we were looking at the effect of adding or subtracting c outside the function. Now I want you to notice that the addition or subtraction of c is happening inside the function, inside the parentheses. Let's take a look at an example. So here we would like to graph the function f of x equals the absolute value of x, and then g of x equals the absolute value of x minus 2. Now, I'm not going to do all the work here since we did most of the work on the previous page, so I'm going to import that work here. So here is the graph of f of x equals the absolute value of x. And now let's graph g of x equals the absolute value of x minus 2. So for this, when you plug in a value, such as when you plug in x equals negative 3, g of negative 3 is the absolute value of negative 3 minus 2, which is the absolute value of negative 5, which is 5. And we go through that same procedure for all of these numbers here. So when you plug in negative 2, you should get 4. When you plug in negative 1, you should get 3. 0 should give us 2. 1 should give us 1, and 2 should give us 0. And when you plug in 3, you should get 1 again. Now let's go ahead and graph these points. So we have the point negative 3, positive 5, which is up here. Negative 2, positive 4. Negative 1, positive 3. 0, 2. 1, 1. 2, 0. And 3, 1. And you should be able to see the V shape here. You can see that we've come down like this, and now we have our V going back up like this. Let's sketch this graph. And what you should notice with the graph of G is that it has the exact same shape as the graph of F, except that we took the graph of F and we shifted every point to the right 2 units. Every point is getting shifted to the right 2 units. And that is because we have x minus 2 inside the parentheses. Now, it's very typical for students to want to associate the negative here with moving to the left. That seems to make more sense. But the reason it gets shifted to the right is because it is when you plug in positive 2 that you get 2 minus 2 is 0. So for the y value to be 0 on the original graph, we have to plug in x equals 0. For the y value to be 0 on the new graph, we have to plug in x equals positive 2. So that's why it's shifting to the right 2 units. Now we're going to talk about combining vertical and horizontal shifts of a function. So for the first function here, we want to graph g of x is equal to the square root of x plus 2. So let's remind ourselves what the square root graph looks like. So here is what f of x equals the square root of x looks like. So when we graph the square root of x plus 2, the plus 2 is on the inside of the function. So this is going to move the graph left 2 units. So the graph of g, I can get that by simply taking each point that I have on f, and these are the main points that I have there, and just moving them 2 units to the left. So if I move the point 0, 0 to the left 2 units, we get this point. If I move the point 1, 1 to the left 2 units, we get this point. And if I move the point 4, 2 to the left 2 units, we get this point. And if I simply connect those, you can see what the graph of g of x looks like. Now let's look at the other function, part b. So for this one, we need to start by graphing the function f of x equals the absolute value of x, because you can see that this is a variation of that function. And so the absolute value of x looks like this. And now to graph g of x, we just need to realize that the plus 3 inside the absolute value will shift the graph to the left 3 units, and the negative 2 on the outside is going to shift the graph down 2 units. So if I take every point on this graph here, and I shift it to the left 3 units and then down 2 units, we will get a new graph. So let's think about starting with the point 0, 0. If we shift that point to the left 3 and then down 2, this is where that new point will be. So we'll put a point here. And then just pick a couple of other points. And it could be any points on the graph. So if I take this point here, which is 3, 3, and I shift that point to the left 3 and then down 2, that puts us at the point 0, 1. And then let me just pick one more point here. Suppose I pick the point negative 2, positive 2. If I shift this point to the left 3 and down 2, that will put us at this point right here. And from there, you can get a relatively accurate sketch of what that graph would look like. And so this is what the function g of x would look like. So this is a combination of a horizontal shift and a vertical shift. Next, we're going to talk about vertical scalings of the graph of f of x. So if we know what the graph of f of x looks like, let's say f of x looks like this graph here, then if you take that function f of x and multiply it by a number, that is going to stretch the graph vertically if that number is greater than 1, and it's going to shrink that graph vertically if the number is less than 1. So again, if I know the graph of f of x, multiplying by a number greater than 1 is going to stretch it by that factor. Multiplying it by a number that is less than 1 is going to shrink it by that factor. So let's go ahead and take a look at an example. And by the way, you'll see the language here. They'll say that when you multiply by a number bigger than 1, you are stretching the graph vertically. And when you multiply by a number less than 1, you are compressing the graph vertically. Let's go ahead and take a look at one more thing here, and then we'll do an example. The other thing that you can do is you can take a function and multiply it by a negative. When you multiply a function by a negative, all it does is reflect the graph across the x-axis. And that is simply because everything that used to be positive, when you multiply it by a negative, will now be negative. So it has the same sort of shape. It's a mirror image here, but it's points on the other side of the x-axis. So just to make sure you understand that, suppose we had a graph of f of x that looked like this. If we were to graph negative f of x, what it would do is it would flip all the points across the x-axis. So these 2 points on the x-axis would stay the same. The points that are below would be shifted to being above. And the points that were above are going to be shifted to being below. And so that is what negative f of x would look like. Now let's take a look at an example. So in our first example, we would like to graph g of x equals 3 times the square root of x. So let's go ahead and bring in the square root graph. And now if I want to graph 3 times the square root of x, what the 3 does is it stretches the graph vertically by a factor of 3. And what it basically means, what the 3 does, is it makes the graph 3 times as tall. So when I have the point 0, 0, that's still going to be 0, 0, because 3 times as tall as 0 is still 0. But this point here, where it's x equals 1, y equals 1, now that's going to be 3 times as tall. So 3 times as tall as 1 is 3. So that point would be up here. And then this other point, which is the point x equals 4, y equals 2, is now going to be at x equals 4, y equals 6, because 3 times 2 is 6. So that point gets shifted up here. So the graph of 3 times the square root of x looks like that. And so all we've done there is we've stretched that graph vertically by a factor of 3. Now let's look at the next one. We have negative 2 times the absolute value of x. So let's go ahead and bring in the absolute value graph. And now we just need to understand, what does multiplying the absolute value function by negative 2 do? Well, the 2 will once again make it twice as tall. So we know it's going to be twice as tall. But the negative also reflects it over the x-axis. So the point 0, 0 is still at 0, 0. But let's just consider the point 1, 1. When we're at the point 1, 1, the 2 is going to make it twice as tall. So that brings it up here to 2. And then the negative flips it over the x-axis. So now it's going to be at this point here. Let's pick another point. Suppose I take the point 2, 2. What does that look like? Well, again, the y value gets twice as tall, so now it's going to be up here at 4, but then it also reflects over the x-axis, which drops it down to negative 4. So this is what that side of the graph looks like. And the other side looks the same. So the point negative 1, positive 1, if I multiply it by 2, it gets twice as tall, and then the negative reflects it down across the x-axis. And I could do the same thing for the other point there, and this is what g of x will look like. And then for our final example, you can see that we have an absolute value function, and we're doing 3 things to this function. We are moving it to the left 1 unit, and then we are multiplying it by negative 2, which is going to make it twice as tall and also reflected across the x-axis. And then the last thing we're doing is we're adding 3. So let's take a look at what happens to that, and we'll do this sort of in a sequence of events. So first, let's bring in the basic function. So here is what y equals the absolute value of x is going to look like. Now I'm going to do this in a sequence of events so it's a little bit easier to understand. Once you get the hang of this, you can do this all in one step. So the absolute value of x plus 1. First, let's just think about what would that look like if that's all we were doing. We know that this is going to move the graph to the left 1 unit. So if I take every point on this graph and I move it to the left 1 unit, we end up getting this graph here. Now what I'm going to do is take a look at the next thing that happens to this function. So we have the absolute value of x plus 1. Now what would happen if I took that graph and I multiplied it by negative 2? So the next graph I'm going to look at is y equals negative 2 times the absolute value of x plus 1. What that does is it takes the absolute value of x plus 1 graph and it makes it twice as tall, and then it also flips it over the x-axis. So this point right here, negative 1, 0, is going to stay the same. It's going to be at negative 1, 0. But this point right here, which is at 0, 1, gets twice as tall and then gets flipped over the x-axis. So it's going to be down here. Likewise, this point right here, which is supposed to be at negative 2, positive 1, I didn't do a great job of graphing that. Let me fix that. There we go. It's a little bit better. So this point right here, which is at x equals -2, y equals +1, again, it gets twice as tall up there at 2, and then it flips over the x-axis down to -2. So that is going to be this point down here. So here is what that graph will look like. And now the final thing that I need to represent here is what happens when I add 3 now, right? That's the last step. So let's bring in one more graph here. Sorry, I'm running out of room here. And what I'm going to do now is I'm going to take this graph and I'm going to add 3 to it. So my final graph will be y equals -2, absolute value of x plus 1, plus 3. Well, we already know what this graph looks like. That's this graph here. Now when I add 3, that's just going to move this graph up 3 units. So every point on this graph gets shifted up 3 units. So the point here at -1, 0 gets shifted up to -1, +3. And I could pick a couple more random points. The point here, which is 0, -2, if I shift that up 3 units, is now going to be at the point 0, 1. And if I pick the point 2, -2, -2, shift that up 3 units, I get the point -2, +1. And so here is what that final graph looks like. And once you get a little bit more used to doing these things, you'll be able to go directly from the beginning to the end. But I find that when you're first learning about translations, it's often good to just do one thing at a time. And so if you go through it, remember, I started with doing the +1 part first, right? I did that because that's closest to x. Then the next thing I talked about is what does the -2 do? That's what I did here. And then finally, I said, well, what happens when we add 3? So that was the order in which I went through the translations. For this next one, we're going to take a little bit different approach. It says, suppose the graph of a function g of x is produced from the graph of f of x equals x squared. And then they describe how this happens. So we're going to vertically compress the graph of f by a factor of 1/3, and then shift it to the left by 1 unit, and finally shifting it downward by 2 units. Give an expression for the function g of x, and sketch the graph of both functions. So we start with f of x is equal to x squared, and then we're going to change that into g of x by transforming x squared by doing what they asked us to do here. Okay, so to vertically compress the graph by a factor of 1/3, it means we're going to multiply x squared by 1/3. So if that was the only thing we were doing, then this is what g of x would be, okay? And actually, I'm going to change this to y equals, because we're just not quite done yet. So we've taken care of compressing it by a factor of 1/3. Now we're going to say, how would you then shift it to the left by 1 unit? Well, to shift it to the left, we have to add 1 to x inside the parentheses before we square it. So we would still have the 1/3, but now instead of x squared, we're going to have x plus 1 squared. And that takes care of shifting it to the left by 1 unit. And actually, let me do that in red so it matches. There we go. And finally, we want to shift the graph downward by 2 units. How do you shift something up or down? Well, pretty simple. All you have to do is add or subtract the number outside the function here. So the final thing we're going to take what we have in that last step, and then to shift it down by 2 units, we're going to subtract 2. And this is what g of x would be. G of x would be 1/3 x plus 1 squared minus 2. And now they want us to graph both functions. So let's bring in a couple of graphs, and then we'll graph both functions. So first I'm going to graph f of x equals x squared. F of x equals x squared is a really simple graph. We should all kind of have this graph memorized because we do graph this function quite a bit. But it's basically just a parabola that looks like this. All right. Now, how do we graph g of x, which is all of this stuff? You can do it all at once if you want. So let's just start by thinking about where is this vertex going to go in the new graph? Well, we know that every point on this graph gets moved to the left 1 unit and then down 2 units. So this point here is no exception to that. If we move it to the left 1 unit and down 2 units, this is what we get. And I don't have to worry about the compression of the graph because y was 0 to begin with, so nothing's going to change there. It's just going to get shifted around. Now let's take this point up here. I want you to notice that the y value here is 9. When we vertically compress it by a factor of 1/3, that's going to make the y value only 3, okay? And then now we're going to shift that number to the left 1 and down 2, and that's going to bring us to this point right here. Okay, so again, what I did is I picked a y value on the original graph, and I picked 9 because 9 is easy to multiply by 1/3. 9 times 1/3 is 3. That brings us down to this point here. That takes care of the compression. But then we have to shift that point to the left 1 unit and down 2 units. And then I can do the same thing with this point up here. If I vertically compress that by a factor of 1/3, that's going to bring it down to this level here, right? Because 1/3 times 9 is 3. And then I shift that to the left 1 unit and down 2 units, and that brings us to this point right here. And then now I can just sketch a graph. It doesn't have to be perfect, but that's basically what g of x will look like. The last thing I want to talk about is a horizontal scaling of the graph of f of x. And this is the least common thing that we do, and sometimes is the hardest one to understand. But if I know the graph of f of x, if I multiply the variable x by a number c that is larger than 1, that is going to compress the graph horizontally by a factor of 1/c. And if I multiply x by a number c that is less than 1, that is going to stretch the graph horizontally by a factor of 1/c. The other thing is we can talk about reflecting a graph across the y-axis. So if you form a function g of x by plugging negative x into the function, that simply takes your function f of x and flips it across the y-axis. Now, I know that this probably doesn't make sense just to state these things, so let's do an example. So here we have a graph of f of x, and this is our graph of f of x. And what we want to do is use this graph to sketch the graph of f of 3x. So what we need to do is we need to remember, what does the 3 do when it's inside the function being multiplied by x? Well, what it's going to do is it's going to compress your graph horizontally by a factor of 1 over this number. So that'd be 1/3. Now, what does that mean exactly? Well, if you look at your graph here, it means that with every point that you have on that graph, it's going to get multiplied by a factor of 1/3 horizontally. So this point right here is at x equals 3. If I compress that by a factor of 1/3, 1/3 times 3 is equal to 1. So that point is going to get compressed to this point here. Likewise for this point is at x equals -3. If I compress that by a factor of 1/3, 1/3 times -3 is +1. Now, anywhere that x is already 0, nothing happens because it's already at x equals 0, right? So when you compress 0 by a factor of 1/3, you still get x equals 0. So that's this point here. So what that graph looks like, f of 3x, looks like this. So notice that it's the same as the graph that we started with, but it's been compressed. It's been compressed horizontally inward by a factor of 3. All right, now let's think about what happens to the second part. What does f of negative x plus 1 look like? So now we're not compressing the graph. Instead, we are taking the opposite of x. And what that does, if you remember on the previous page, f of negative x reflects the graph across the y-axis. So to see what this does, we have to do two things. We have to take all these points that we had originally, we have to reflect them across the y-axis, and then we also need to shift the graph up 1 unit, right? Because the plus 1 shifts the graph up 1 unit. So let me erase the old stuff that we had here. First, let's just think about what does f of negative x look like. Well, f of negative x is going to take every point and reflect it across the y-axis. So this point over here gets reflected over to this side. This point here gets reflected over to this side. And this point stays the same. And all these points here also get reflected over. So you end up getting a graph that looks like this. Now, I know that's a little bit cluttered, so what I'm going to do is go ahead and put that over on my axis to the right. So this is what f of negative x would look like. Now I need to do the plus 1 part. So the plus 1 part is just going to take this graph and shift everything up 1 unit. So the graph of f of negative x plus 1, we're going to take this point here, shift it up 1 unit. This point in the middle, shift it up 1 unit. And this point on the other end, shift it up 1 unit. And then just connect those 3 points. And this is what f of negative x plus 1 will look like. So the whole point with this section is that you can graph transformations of known graphs, not by plugging in x values and finding y values, but rather by understanding how things can be reflected or shifted in certain directions to easily be able to get new points for the new graph.